Hello everyone, this is Dr. Zach. For today's lesson preview, you're to find the similarities and differences for these integration problems. How do we know which direction to take when we're getting ready to integrate? Think about the structures and go ahead and try to integrate our first three questions. Okay, so did you notice in our first problem that the denominator has an exponent that is greater by 2 than the numerator's exponent? And whenever that happened before, some arctan was involved in your integration. For the second problem, the structure of the problem has your denominator with an exponent 1 larger than the numerator. Whenever that happened, you should get a natural log somehow involved in your integration. All right, now for your third question, did you notice that the exponent's denominator and the exponent in the numerator were equal? There might be some long division involved or factoring perhaps, something algebraic to simplify each problem. So back to the first question. You should recognize this pattern as the integral 1 over x squared plus a squared. You are to know this formula. Sometimes you just gotta know what your answers are going to be from their formulas. For our second problem, we have a u substitution. U is equal to your x squared plus 9. Du is equal to 2x dx. Go ahead and finish that problem. The third question. So did you remember how to do some long division? And if you did your long division, you can do synthetic. I don't care. As long as you are able to rewrite this problem as the integral of 4 dx plus the integral of 36 over x squared plus 9 dx. So now you have an arctan for the second half of your problem, and the first part of your problem is a very simple little integration. All right, now we're going to mix our rules together. Just never know what you're going to run into. For example 1, look at the structure of your problem. If you try u substitution, u might equal 4 minus x squared. So your du would be a lovely negative 2x dx. We still have a 3 in the way. That's a problem. But you know what? Let's split this into two problems. We have the integral of x over the square root of 4 minus x squared dx plus the integral of 3 over square root 4 minus x squared dx. So sometimes when you take a complex problem and split it into two little problems, then you can figure out that this isn't as hard as you thought. You're going to use u substitution for the first part of your problem. The second one is a structure that you should recognize. And the rule that you want to use has to do with the integral of 1 over the square root of a squared minus x squared dx is going to be equal to, in this case, it's the arc sine of x over a. So go ahead and finish up example 1. For example 2, now there are several ways to do this, and I hate to tell you one way to do the problem, but since this is a video, you get to see what I'm going to do. All right, so if I try u substitution and I let u equal 1 plus e to the x, du is going to be e to the x dx. So that's not very useful. I would need to have an e to the x in the numerator, and as you can see, there's just a 1 in the numerator. Well, how clever could we be? If I were to try long division, yeah, I'm not really sure how that's going to work, but it will work. 1 plus e to the x gets divided into 1. I think it's an insane way to do it, but I have seen students do it that way. You go ahead, give it a try. Not my favorite way. My favorite way is to multiply by e to the negative x over e to the negative x. And let me tell you why. Well, when I did my u substitution, I noticed I'd like to have an e to the x in the numerator. You can't have one. But if I multiply through by the value e to the x over e to the negative x over e to the x, I get e to the negative x in my denominator plus, think about it, what is e to the negative x times e to the x? If you said 1, you are correct. And then you can try u equals e to the negative x plus 1, and your du is equal to negative e to the negative x dx. From here, you should be able to finish this problem. Again, there are many algebraic ways to solve this problem. This is my favorite way, though. All right, now what about number 3? As you look at number 3, I don't know the antiderivative of tangent squared, and you know what? You don't either. But what you do know is, I don't know, how about a trig substitution? Do you know anything about the tangent squared theta? What does that equal if you did a trig identity? Hopefully you know that it is the secant squared theta minus 1. And if you don't know your trig identities, this is a good time to brush up on them. So now we will rewrite our problem as the secant squared. The angle is 2x minus 1, and then that is multiplied by dx. So what did we do? We used a trig identity in order to substitute. All right, but again, you have to know your basic integration formulas. If you don't know what the antiderivative of secant squared is, you are in trouble. All right, you need to go back and figure those out. You do know, though, that the derivative of the tangent is the secant squared. So what if we were to say the antiderivative of secant squared is equal to the tangent? And since it's the tangent with the angle 2x, it's going to be 1/2 tangent 2x. Of course, we've got minus 1, and that antiderivative is x. Don't forget plus c. All right, so we now have 1/2 tangent 2x minus x plus c is our antiderivative. Know your trig identities. So, what do we need to know when we're integrating? You must know your basic integration formulas and problems. Look for u substitution to start. Know your algebra. Think about long division, clever multiplication. Wait, you can even add and subtract the number 0. You could expand the problem, multiply it out, separate the numerator so that you have 2 different problems. Ooh, completing the square, that might show up. Use your trig identities. And of course, multiplying or dividing by a conjugate is sometimes very fun. Next, you're going to practice many types of these problems. Be on the lookout for all of these integration ideas. That's it. Have a great day.